Well, are we ready to go?
There you go.
All right. Well, I thought this was really funny, but we have no time for humor because we're behind schedule. But the response of Pi to his wife's criticism is to complain that she's a square, and a low-down square at that. And there's much other humor in the slide, but if you could give us the next slide, we have to go on. And go ahead with the next slide. I'm going to talk about Baily's bead. It's my perspective on Baily's beads. Go ahead and show the next slide. And I want to illustrate it with an observation I made 13 years ago. In the outback eclipse of 2002, December 4th, I set up near Woomera, South Australia, in the desert, and made a southern limit observation of Baily's beads. Next, please. I set up 4 telescopes. Each of them was a Moxitov of 70 millimeter aperture, and they shared a single mounting. 3 of them had neutral density 3.8 full aperture filters. Those let through approximately 1/9,000th of the light from the sun. And of those, with those 3, each had a narrow bandwidth color filter. One had a 650 nanometer red filter, 550 nanometer green filter, and the third one had a 450 nanometer blue filter. In addition, the 4th telescope had a neutrodensity 5.0 full aperture filter that lets through 100,000th of the light from the sun, and it does emit IR and UV in addition to the visible spectrum. It was on a clock drive with a hand controller for fine adjustments, and I had 4 PC-23 video cameras from a Super Circuits company. Next slide, please. And just go on to the next slide. This shows the setup fairly well, although this slide, I didn't take a camera to the outback, so I don't have a picture of my setup, but this was taken at a later setup in 2012 for the May 20th annular eclipse in California. And you can see I have 4 telescopes on a single mounting, and they have little adjustment screws so I can point them in exactly the same direction. They have full aperture filters. In Australia, what we're talking about today, I had identical 70 millimeter aperture telescopes, but for the annular eclipse I used 4 different apertures. This is balanced in 2 axes, it's clock driven, and there's a hand controller. Next slide, please. And this is my truck, and this is the setup in California, and you'll notice I have 4 boxes with computers hidden inside them, and I recorded to virtual dub on 4 different computers. Now this is what I did in California, but at the outback I was not that intelligent, and I recorded on, I used a what's called a quad recorder to feed all 4 video feeds into one device. This is like a security system you find in a business. Nowadays some of them have 32 feeds or 27 or 16 feeds into a single device that then displays it on a single screen. Well, this was a quad recorder that only took 4 cameras, and next slide, please. To record the video direct to the computer. Now we're going to show the video in just a moment, but I just want to sensitize you to some things. We're going to try to show the video a couple times here. It's only 37 seconds. I cut out 37 seconds from the middle of it. Yeah, it's on the video is on the thumb drive as well, so.
Desktop, shares desktop.
Yeah. I may be able to get it from the thumb drive. Okay, it's running.
Yes.
So we have time insertion at the top. You see it's video time inserted. A quad recorder recording all 4 cameras. And then rather than move it by hand, I use a hand controller motor to slide the mounting so that I'm looking at the reappearance side of the eclipse now and watching the reappearances. And we want to run through this again after I explain a thing or two to look for. So that's just 37 seconds from the critical center of the video. But what I want to share with you a couple things. First of all, this is blue, this is green. Yeah, upper left is blue, upper right is green, lower right is red, and I'm sorry, lower left is red, lower right is integrated light. You notice there's a lot of scattered light in the integrated light view. I believe that most of that scattered light is reflected off the back of the full aperture filter. That is, it reflects off the video camera, which has an acrylic surface, and then back to the full aperture filter, and then back into the scene again, and presents as basically a ghost image, and so on in scattering. The red is well focused, and it really makes a nice video. The green is very dark. I'm not sure you can see it well projected in the room, but it has a black background. Ordinarily, if you have a black background of a video or any image, you have to be concerned that you're losing data in the darkness. You need to see the noise of the background to be sure that you're seeing the faintest thing that you can see. And it turns out that in 3 of these, you can see a gray background, so you know you're seeing the faintest beads you can see, but in this one we have a black background. And that's because of the problem with quad recorders and with security systems. You adjust the brightness of each one individually. And what happened is that my image of green looked very bright on my system, and so I kept turning it down. And I turned it down so all the brightnesses of the 4 were equal. And then when I looked at my videotape afterwards, I discovered that what I saw on the display corresponded poorly with what actually was recorded, and I had turned down the green because it was too bright, and I was left with a black background. That compromises data. That's why I say don't use a quad recorder, and in my subsequent observations in 2012 annular eclipse, I didn't use a quad recorder. I had a separate computer for each camera. The problem with the blue is that it's out of focus. You may not have noticed that on the first run through, but now that I've explained all these problems that you get into with recording eclipse Baily's beads, let's run through it again and see what it looks like. The blue is out of focus, the green has a black background, and this one has scattered light. Okay. Now I thought the focus was perfect when I made it. It's just a bugaboo at eclipses to focus properly. You don't. Okay. You don't want to try to move this by hand. You shake it all over when you touch your tripod. And especially a little tripod that you carry halfway around the world, you carry a small tripod you can put into a suitcase. These things are a little bit shaky. And if you touch this with your hand, sooner, later in the thing. I'm going to have to rush through these because I got a lot of slides. Yeah, let's go back to the slides. I have to scroll down to the one that we're at. I don't know if you can see it, but our counselor idolizes equality as manifested by the picture on his desk. And yet he was a dividing sign, so he's divisive by his very nature. All right, so this is a bead near the south pole of the moon, and Excel is nice enough to, this is a live movie analysis of the brightness, and Excel is kind enough to give us a second order power function. Next slide, please. And here's a third order power function. You can fit it with either one, and I'll talk about that more. I think the third order is a little better fit. I might draw your attention to the idea that if you go down here, this is a bead that's reappearing, and the baseline seems to be about here, and then suddenly, boop, it seems to be brighter to me. I wonder whether using iMovie is any better than just eyeballing it. Next slide, please. David Dunham reviewed a lot of solar eclipse observations, did a very fine review, and he's presented this a number of times starting in 2005, and he included the observations from the eclipse that I'm showing you. Next slide, please. And his major conclusions were these. Firstly, the accuracy of the solar radius measurements made by timing Baily's beads is about 0.2 arcseconds. Secondly, the use of filters on telescopes appears to yield a smaller solar radius measurement than direct unfiltered observations yield. He concludes this because of an observer, his son, who pointed an unfiltered telescope at Baily's beads and was able to record them that way with no solar filter. And lo and behold, he found that he could see fainter beads that way than we can see with our solar filters. That's why I set up in 2012 with 4 different apertures to see if the aperture, the light gathering power in otherwise identical equipment, made a difference in our ability to find beads. Thirdly, standardization of equipment is recommended to get results that are consistent from eclipse to eclipse. And fourthly, analysis of historical eclipse observations may help us ascertain whether the solar radius changes. I don't want to comment on these conclusions anymore. Next slide, please. Than to say that I want you to remember the accuracy of Baily's bead observations. Just remember that's 0.2 arcseconds or 200 milliarcseconds. Next slide, please. This is a picture I stole from Astronomy Picture of the Day. It's a picture of the transit of Venus. This is Venus up here. The reason I'm showing it is I want you to notice the limb darkening. The sun is brightest in the center, and as you go toward any edge, you discover that it gets dimmer, and that's called limb darkening. And many astronomers have tried to tackle this issue and see how it darkens and do mathematical equations and correlate that with what they know about the physics of the sun. And you notice that at the limb it's also redder. And so limb darkening, it has a color dependency, and they've made analyses of its color dependency as well. Next slide, please. A couple of definitions will be beneficial as we go on. The limb or edge of the sun has been defined by generations of astronomers as the point along the radius at which the maximum rate of brightness drop occurs. This is also the inflection point of the graph of the brightness along the radius. Secondly, the solar radius at a distance of 1 astronomical unit has been standardized at 959.63 arcseconds, and although measurements have generally been near this value, most individual measurements deviate from it somewhat. Next slide, please. Now, this is the type of data that you get when you measure the diameter of the sun using a CCD camera and a line graph across the resulting image. This is the brightness across the sun, this being the left edge of the sun and this being the right edge of the sun over there. And you notice at the edge of the sun, the curve is very steep. If you measure the slope, you find that it peaks on each edge, and that peak in the slope is used to define the edge of the sun. And we're going to be talking more about the scattered light over beyond the edge of the sun. And I want to point out that that there's a little bit of scattered light beyond what astronomers consider to be the edge of the sun. Next slide, please. This is some data that's been compiled on these measurements made by a line graph across an image of the sun, a CCD image of the sun. And you have to put it right across the center of the sun. Next slide, please. Now, this is supposed to be pink here, far over on the right. That's the column of the errors, their estimates of the errors in their measurements. You notice all of them are 959 arcseconds plus a fraction, and they make this very good assessment of their errors. Next slide, please. Now, I want to point out that the best one, made at Mount Wilson, it claims an accuracy 40 times the 0.2 arcseconds that we are judging we make with Baily's bead observations. And the very worst one down here at MDI estimates that its error in its measurements have 1.3 times the accuracy that we make with our Baily speed observations. However, I want to point out that you'll see this, and so people may poo-poo our Baily speed observations, but this is a false accuracy. It's completely false. If you don't believe it, just look at the accuracy of these two. There's one here in the middle called Antalya, made with two different prisms, and in 1999 to 2000, they estimated the radius of the sun to be 959.03 arc seconds with an error of 0.07, and then in 2001 to 2003, they estimated the radius of the sun to be 959.29 arc seconds with an error of 0.01 arc seconds. And if you look at the sigmas and correspond those things, you discover that they don't even overlap at 2 sigma. So we're not talking about accuracy. We're talking about precision. You can make a very precise measurement that's wrong. Okay? In other words, it's precise, but it's not valid. And so that's the defense I have about Baily speed observations. These claimed accuracies are invalid. Next slide, please. Now, this is a little confusing at first. I want to say, first of all, that on the abscissa is dates from 1975 to 2015, and the red at the bottom is the daily sunspot number, and its ordinate is over here. This gives you the daily sunspot number, so that conveys our solar cycle. And the data that's scattered around the graph then is measurements of the radius of the sun, and they're standardized at 959.63 arc seconds, which is 0, and what this measures is milli-arc seconds above or below that standard value. And what you'll discover is that the solar astrolabe has quite a scatter, and you see its accuracy may not be so great as claimed, quite a scatter, and it seems to have perhaps an inverse relationship to the daily sunspot number. Over here there's some vertical columns. These are made by the Do-Re Sol instrument, which is supposed to be an improvement on other prism measurements, and so it's touted here as one of the best ones to include here. And you notice the spread in their data, and what you discover is that if you take this big column of measurements, each of these is a group of measurements, you can get a confidence interval on it that's much lower than the standard deviation because they've made a great deal of measurements, and thereby they claim an accuracy that's very high. And the blue here, extending from here over to here, the MDI measurement, seems to also perhaps have a subtle variation with daily sunspot number. So I just wanted to acquaint you with the type of data that we're dealing with. And when we talk about the scatter we get in our Baily speed measurements, they are 200 milli-arc seconds, so plus or minus 100, and you see we're in the same error range as many of these other types of observation. Next slide, please. Now, this is from an article by Raponi and Sigismondi in 2011. Our own Richard Nugent, who happens to be in the room today, observed Baily's beads in Uganda. I don't know how you pronounce that name. If it ain't Uganda, maybe it's Uganda. Yeah, who knows? Anyway, he observed this. It made this curve. Now, this is the noise is diminished by summation over intervals, but it's a very nice bead disappearance curve. And using some similar equipment, but excluding more light, I'm not familiar with all the details, a gentleman named Andreas Tegtmeier went to India on the same eclipse and recorded this curve. Now, I think the key to understanding what's going on here is that, and by the way, the timing was earlier, the brightness was greater, the timing was earlier, and he didn't have a tapering off effect, he just stopped seeing them. Richard had a tapering off effect. And I want to say that there is an uncanny resemblance of these two curves, the way they're laid out here, to the line graph across the disk of the sun. And so astronomers look at this, namely Raponi and Sigismondi, and they say, well, the real edge of the photosphere must be somewhere between these two curves. In fact, the nominally corrected radius of 959.63 arcseconds is given by the vertical line to the left of Richard's bead measurements, and we expect maybe to find an inflection point in there. But you see, if that's the case, then we're not really measuring the edge of the photosphere, or are we? Maybe we're measuring something else. That's what I want you to understand. And one of the things that bothers me about this is that this is not from a line graph, and it may be a misuse of Baily's bead observation. That I shouldn't say misuse. I mean, I'm afraid that this is the direction of current research by some professional astronomers, and I'm afraid that it's not a valid use of Baily's bead measurements. Next slide, please. I'll be talking more about it. That diagram is up here in the corner. They concluded there is an inflection point somewhere between the two bead light curves, and that therefore the actual edge of the photosphere occurred somewhere before Richard's observations and after Andreas's observations. Furthermore, they felt that modeling of the limb darkening function can fit a curve between the two disconnected bead curves to find the inflection point, that is, a mathematical model. And furthermore, camera chips with increased dynamic range better than the 256 shades of gray we use would improve our bead observations. I just want to take a moment to say that that's completely mistaken. The 256 shades of gray is not the dynamic range of the camera. That represents the brightness resolution of the camera. The dynamic range is the well depth divided by the electronic noise, which is partly thermal and partly intrinsic to the camera. That's the dynamic range. This is something called brightness resolution, and the two are not the same. And so, and by the way, this was taken from the article. He refers to it as dynamic range in the article. So I'm objecting to his article, if you haven't figured that out yet, and I'm reassured that I know he did something wrong conceptually. Okay, now a color effect is suspected, and this is from other data, and so they recommend studying the beads in different colors. Who's done that? Do you know anybody who's done that? Oh, I'm just 9 years ahead of them. Okay, all right, next slide, please. Didn't change. And it hasn't suggested that it wants to.
Sometimes there's a little delay, and then if I wait, I can be patient. Stop.
There you go. Next one, yeah. There you go. I just wanted to say I certainly agree with their number 4. A color effect is suspected. Next slide, please. All right. Now, the fundamental problem with this approach is that it is a way of using the inflection point to interpret Baily's bead observations. The inflection point was made from a line, a single pixel width line across the center of the sun. A Baily's bead is not that. In fact, it's much wider in the bright part than it is at the bottom part. It's not a single pixel wide. Furthermore, it's not a point on the surface of the sun. It's the summation of all the points from the bottom of the gap between the mountains on the moon to the top of the gap between the mountains on the moon. It's not the same type of data. And we should be very cautious in using an inflection point in Baily's bead data to determine where the limb of the sun is. Next slide, please. Baily's bead timings are measuring something qualitatively different from the inflection point measurements. Next slide, please. All right. This is the edge of a line graph across the disk of the sun. This is the edge of it This is the rapid fall off region. The first derivative is over here, showing the point where the slope is greatest, so that determines the edge of the sun. Next slide, please. There is an uncanny resemblance between this little Ditzel curve that's scattered beyond the edge of the sun and our Baily speed measurements. So what is it that causes the reversed curve at the low end of the brightness? What are the things that affect it? I want to review that. Next slide, please. Contributing causes. Remember, I'm talking about a line graph across the disk of the sun. First of all, a color difference at the limb could cause this. Just imagine that the limb of the sun is red, and that every other color has dropped out, and there's just a little bit red left. And if you go a little further from the photosphere edge, you get a longer wavelength red. It'll sort of taper off. At least conceivably could. Next slide, please. Now, these are graphs of limb darkening function. These seem to resemble the line graphs across the disk of the sun, and I want to point out to you that these are graphing something completely different. The abscissa is wavelength, the wavelength of light, and the ordinate is the radius of the sun. And these are 5 different graphs of the limb darkening function, and they were made first in 1973 and the last one in 1998. This was 73, the one at the bottom is 98. And if you look at the graph, you realize that at longer wavelengths, the radius of the sun is greater, and that is to say the edge of the sun is red. Next slide, please. Since the radius varies with wavelength, there may be color effects at the limb. Next slide, please. All right, now this is my modification of a chart from Skylab data, and this is widely published by NASA. The thing I want to point out first is that this is the interior of the sun, which is opaque. The photosphere is not a layer like paint on a wall. It's 400 kilometers thick. And the photosphere is the transition zone from no transparency to complete transparency, essentially. Okay? The transition zone is 400 kilometers thick. The photosphere itself. No, it's 400 kilometers thick. Okay, this the altitude is over here, and this goes from 0 to minus 400 kilometers. So the thickness of the photosphere is 400 kilometers. Okay, and then above it is the chromosphere, which has a thickness of approximately 2,200 kilometers. And then above that is a transition zone, which is a couple of hundred kilometers thick. And I just don't want to take time right now to explain the other things. I'm going to explain them in a moment. But I want to point out to you that you might intuitively think that since the temperature declines from the deep layers of the photosphere to the superficial layers of the photosphere, temperature is on this line, this solid white line. That's the temperature. The temperature declines as you come out of the photosphere. You might think that the superficial layers of the photosphere look red and the deeper layers look violet. Next slide, please. The data shows exactly the opposite. The problem with that thinking is that only the red light from the deeper layers of the photosphere can penetrate to the surface. And in fact, most of the red light we get to the sun is from the brighter, deeper layer of the photosphere. And most of the violet light is from the superficial layer, because the violet light penetrates the photosphere the least well. And so it's exactly the opposite of what you might think. Now, the significance of this for Baily speed observations is that if we're considering looking at the very edge of the photosphere, we might not find that it's red after all. We might find that it's blue. Next slide, please. All right, so I'm looking at contributing causes to that extra light at on the line graph. I want you to be thinking about the line graph across the disk of the sun, and there was a little scattered light at the edge. And I said the first possibility is that there's a color difference at the limb. Secondly, that there might be atmospheric scattering and imperfect seeing. Next slide, please. On the left is some different point spread functions. We measure them with something called the Fried parameter, which is this R0 value. You don't need to know that, but this is different point spread functions related to atmospheric scattering. And the worse the seeing, the more scattering there is of light, the more light you get scattered out beyond the limb of the sun on your line graph across the disk of the sun. And when you get that light, where do you think it comes from? It comes from up here, up in the middle, and it turns out, next slide please, oh, okay, well, okay. Let me just say that it turns out that when you scatter light beyond the photosphere and the line graph across the disk of the sun, that you move the inflection point toward the center of the sun. So you get a smaller radius for the sun. So the line graph measurement is dependent upon the atmospheric seeing. A third contributing cause might be diffraction. Might that be diffraction causing scattered light out past the edge of the photosphere on a line graph? I think this room is sufficiently brightly lit that you probably can't see that there's a great big airy disk in the middle of this picture. And over on the left we have a small airy disk, and this is just to illustrate that there are two different sizes of airy disks, and the size of the airy disk by calculations has been shown, like atmospheric seeing, to scatter light beyond the edge of the photosphere on a line graph across the disk of the sun, and thereby move the inflection point the other direction. Next slide please. I've already stated this. Next slide please. And I've stated that. Next slide please. All right, another cause of scattering of light on a line graph beyond the edge of the sun is pixelation of the image. Next slide, please. This can be a little difficult to understand. If you measure across the center of the sun, straight across on a single row of pixels without ever crossing the row, then we're going to say you have a 0 degree, no tilt of your line graph. And you get a measurement right in the middle there. But as soon as you start tilting it and crossing rows of pixels with your line, as you make a line graph, you discover that the solar radius measurement increases. And it increases stepwise with further and further distortions of the direction of measurement, and then suddenly drops way down there, and you get this repeating pattern. And this sounds like a subtle effect until you look at the ordinate of this graph and you see that the variation caused by changing the angle of your line graph is 2 arc seconds. That's a lot. You see what I mean? This is a very significant effect. You have to do this right or you'll have a mistaken measurement. Next slide, please. All right, and finally, with regard to a line graph across the sun, maybe that little light beyond the photosphere is due to seeing the inner region of the chromosphere. Next slide, please. Now, I showed this out before. I want to point out two things. On this graph of the diagram of the outer reaches of the sun, the temperature is the solid line that goes up and curves, and you notice the top of the chromosphere is approximately the same temperature as the photosphere, but the inner part of the chromosphere is cooler, and you therefore might think that the inner part of the chromosphere isn't as bright. The temperature abscissa is here at the bottom, and note that it's a logarithmic function. The density is the dotted line, and the density goes up and doesn't diminish much until you get outside the photosphere, and then rapidly diminishes through the chromosphere and through the transition region, and then not much in the corona. The density abscissa is at the top, and it is also a logarithmic function. Now, what you'll notice, it's actually a power function. What you'll notice, I need to go back, is that the density down here at the bottom of the chromosphere is about 1,000,000 times the density at the top of the chromosphere. And that's more than enough to make up for the lower temperature. In other words, you might think that because there's a lower temperature in the inner regions of the chromosphere that it won't radiate as brightly. In fact, it's 1,000,000 times as dense as the outer regions of the chromosphere, and therefore it radiates much more brightly than the outer regions of the chromosphere radiate. Next slide, please. All right. Now let's see how much of this can be applied to Baily's beads. I've been analyzing a line graph across the disk of the sun. I've been looking at sources of error in that measurement, and I want to see if some of that can be applied to this peculiar line that has an uncanny resemblance to the edge of that line graph. Next slide, please. We're thinking of Baily's beads now. This is what we got from my previous discussion. Next slide, please. And some of them don't apply to Baily's beads. A color difference at the limb would make a difference in Baily's beads. That might account for that gradual tapering off. Atmospheric scattering and imperfect seeing will give us noisy data, jumping brightness, but it won't cause a failed observation with scattered. It won't cause that type of scattering. Diffraction will be effective with Baily's beads, but it's a different source of diffraction. It's not diffraction due to the aperture of the instrument. It's diffraction by the knife edge effect of the edge of the moon. And might we be seeing diffracted light from the photosphere around the edge of the moon when we measure Baily's beads? Pixelation of the image won't be a factor when we measure Baily's beads, but the bright inner part of the chromosphere is certainly a possibility. Maybe the reason we're seeing that gradual tapering off of the Baily's bead beyond what must be an inflection point somewhere in the brightness of Baily's beads has to do with really measuring the chromosphere rather than the photosphere. Next slide, please. There is one more possibility. We could see me scattering by electrostatically elevated dust at the lunar limb. Now we know this isn't the case, and I'll get to that shortly. Yes, Tony?
Roger, the concept of seeing the chromosphere, I think is very valid because we did a observation of the Mercury transit, and we had a chromosphere telescope set up, and then a white light filter telescope set up, and I call it first contact on the chromosphere way earlier before anybody could see it in white light.
Yes.
And so...
That's right. You had an H-alpha, probably an H-alpha filter, and it shows the chromosphere well, and that during the Mercury transit, it looks like it's invading the photosphere when it's actually the chromosphere. Tony, for those who are online and can't hear you, I'm just trying to repeat what Tony just said. He pointed out that when you use an H-alpha filter and observe a Mercury transit, you can mistake the edge of the visible part of the chromosphere for the photosphere of the sun, and thereby call the first contact at the improper time. So. That's right, yeah, okay. Me scattering is one of the reasons I actually set up. When you do, I had curiosity about the colors of eclipses, and I really wanted to see whether I could explain the visibility of the chromosphere due to me scattering. Next slide, please. All right. But each of these possibilities might be investigated by studying the beads in multiple narrow wavelengths and by spectrographic video. Next slide, please. In my opinion, it is premature to measure the solar diameter, and it is premature to try to optimize equipment for that purpose until we know what we are measuring. Next slide, please. We missed something. You skipped to... There's the next slide. Let's see if there we go. Once we find what we're measuring, we may find that optimal equipment is considerably different from what we have been thinking. And that's an important concept, and that's really what I want to get at today. Next slide, please. Okay, if there's a color difference at the edge in our Baily's bead measurements, talking about Baily's bead measurements now, not that line graph, we don't know whether it will be bluish versus reddish. Next slide, please. Remember, I showed you with the Skylab data, it suggested that the edge of the photosphere might be blue. Next slide, please. While the limb darkening equations suggest that the edge of the photosphere should be red. Next slide, please. It should show absorption lines. If it's due to a color difference, we're looking at the photosphere, and the photosphere should show absorption lines rather than emission lines. Next slide, please. This is data from Campbell in 1906, 109 years ago. And, Campbell is best known for something he did about 20 years later when he got much better data than Eddington did. And Campbell confirmed general relativistic effects on the light passing the sun during a solar eclipse. That was 20 years later, but his previous eclipse observations, let me just point out here, at the bottom is the solar disk, and you can see this is a high-resolution spectrum with multiple absorption lines. That was from the disk before the eclipse. At the time of the eclipse, he had a gradient filter in addition to his diffraction grating, and that gradient filter allowed him to have various sensitivities at different levels across his field. And the photosphere showed absorption lines that were subtly weaker than they were in the solar disk before the eclipse. The inner chromosphere, you'll notice, shows weak absorption lines as well as emission lines. So we can't just say that the dividing line between the photosphere and the chromosphere is where absorption lines change to emission lines. It isn't that clear. The inner chromosphere shows both, and the outer chromosphere just shows emission lines. If you, let me just say that you may notice that some of the absorption lines from the photosphere do extend into the continuum of the inner chromosphere, and some of the emission lines, this tallest one here, which I think might be calcium, I say that because it's at about 4,700, extends all the way, this emission line, all the way down into the chromosphere. So you can see then that if you were to try to choose say a hydrogen line or a emission or absorption line that's quite prominent and a narrow wavelength to measure the diameter of the sun, your measurement would be erroneous because you chose that line. What you want to do instead is measure the continuum, not the emission line itself. And if you try to use the point of change from emission to, going from photosphere to chromosphere, from absorption lines to emission lines, you're still going to have a blurry point of change because that point is not crisp. I think you can see that on this slide. Next slide, please. All right, now it may be hard to see, but there are two figures that I added right up here. Campbell concluded that the continuum of the inner chromosphere, all the way to the inner chromosphere, was about 1,000th the brightness of the center of the sun. And he can, in adding all the emission lines of the outer chromosphere, because the continuum of the outer chromosphere was not visible to him, just adding all the emission lines, he concluded that that was 1/10,000th the brightness of the center of the sun. Now those figures are significant if you're trying to plan an eclipse observation. You say, just how much solar filtering do I need to see emission lines and absorption lines in the inner chromosphere? Next slide, please. All right, back to our Baily's beads. What will color difference at the edge do? Its change over time should follow a power function. And I already showed you a couple power functions. Next slide, please. For those of you who like to do analysis, you can take a U-shaped gap and a V-shaped gap, and you can assume that as the sun rises here, you can see that the bead gets brighter, and the brightness in a U-shaped gap will change as a constant times x squared plus x, and a V-shaped gap will be a constant times minus x cubed plus 3x squared plus 2x. There's an error on the slide. There should be a minus sign in front of the cubic parameter there. And so where x is the number of the video frames, most of you probably are not interested in analysis, and so you wouldn't do this kind of thing. But I just wanted to point out that you get a power function and that it's going to be square or cubic, and if you have a coefficient in front of the cubic factor as a intermediate between 1 and 3 times that in front of the squared, then you might think that you have a gap that's intermediate between a U-shaped and a V-shaped gap. Next slide, please. And I showed you this. This is the power function where power of 2. Next slide, please. And this is a power function where the power is 3, and it turns out the coefficient is very low, so this may be an intermediate type gap. But this gives, I think, a little better point of appearance. Next slide, please. All right. Now, let's suppose that with Baily's beads, we're looking at diffraction of intense solar light by the limb of the moon. It'll be brighter in red. because red light is diffracted at a greater angle than blue. By the way, this is a much greater effect than you get by refraction. The difference in refraction between red and blue is much less than the difference in diffraction between red and blue. And I say this to point out that it'll be very red if it's diffracted light from the photosphere. Next, and the spectral lines of absorption should be visible because it's photospheric light that's diffracted. And narrow bandwidths conceivably could show a fluctuating intensity if we can control for atmospherics. Next slide, please. I want to show you one of my bead. Oh, okay. Just imagine, I hope you can see the peaks and valleys of the diffraction here. This is from shining a laser at a CCD, and the part on the right is the zero order intense laser light, and there's a knife edge vertically to its left, and beyond the knife edge we get all these peaks and valleys in brightness. That's what we could be observing in Baily speeds. Next slide, please. And this is one of my beads from that eclipse. And it goes up and down and up and down and up and down and up, and then it goes blah, 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 before it finally blinks out. And, you know, this is probably atmospherics. But what if it's diffraction? You know, we need to know. Next slide, please. All right, now if we're looking at the brighter inner part of the chromosphere with Baily speeds, it will be redder than the photosphere. The spectrum will show emission lines more strongly than absorption lines, probably. And it seems to me that if we witness the disappearance of the photosphere, we may find a step off there of some type in brightness and so on before it finally disappears. But I don't know about that. I just think it's interesting to contemplate it. We need more observations. Next slide, please. And if it's forward scattering from electrostatically elevated dust on the lunar limb, the color will be the same as the photosphere. It won't have a color effect. The spectrum will show the photosphere's absorption lines, and the fall off will be very gradual with time, and it should last as long as the eclipse. Now, me scattering, although it can be fairly narrow, it turns out that the angular difference during an eclipse is not going to be sufficient to make a rapid fall off in the brightness of the bead. And so what we see with Baily's beads is inconsistent with forward scattering. Next slide, please. So I've summed that up here, and I just bring this to your attention to point out that some observations, for example, seeing strong emission lines would strongly suggest we're looking at chromosphere, and rapid fluctuations might suggest that we're looking at diffraction, particularly if it's very red. If we see blue at the limb, certainly that would be a colored solar limb. If it's red, it could be any of these three. And, but isn't this interesting that we might be able to figure some of this out? Next slide, please. All right, this is my data from the eclipse, and it's a little confusing, but the occult program by David Harold gives you a readout, one of which isn't included here. It gives you the small d stands for difference, okay? Difference in right ascension. It says, was the sun where you thought it was? It gives you a difference in declination. Was the sun where you thought it was? It gives you a difference in radius. It does all this by nearest fit, least squares nearest fit of your Baily's bead observations to the known limb of the moon. Well, there's a problem with accepting the difference in declination. Why should I believe there's a difference in declination varying among my four telescopes when they're all made from the same location? So there is no real difference in declination. This is not correct. And by the way, I didn't even include difference in right ascension because it's negligible. So, but there's a correction factor related to the relative motions of the sun and the moon and the cosine of the angle between the two and stuff. And it turns out that if you multiply these numbers by about 0.99, and then you subtract it from the calculated difference in radius, you get the corrected difference in radius. And guess what? The difference in radius, that is the deviation from the predicted radius of 959.63 arc seconds in integrated light, which includes infrared, was 0.7 arc seconds. An error on the slide, these are 650, 550, and 450 instead of 600, 500, and 400 on the left. But anyway, in red light, it was 0.48, in green light, 0.31, and in blue light, 0.26. Now, this needs to be repeated. And one of the reasons, here's two reasons it needs to be repeated. The green had a black background. I might have missed some of the brightness of the beads. The blue was out of focus. Now I think it did pretty well, but I might have missed some of the brightness of the beads because it was out of focus. So this is a nice result, but it's easy to challenge it on the basis of the things that I pointed out. Next slide, please. Yeah. I focused to the best of my ability, and it just wasn't good. You know. And at eclipses especially, it's really very hard to focus on the crescent sun. All right. So factors related, here are my recommendations. Pardon? Yes. I did it after I set up my equipment, and I'm pointing at the crescent sun with the blue filter on, focusing to the best of my ability. Okay? That's what happens. And let me tell you, at eclipses, that's hard. If any of you have ever done an eclipse video, you know it's hard to focus. You don't get to focus on a Baily bead, you see. When they appear, you've missed your opportunity to focus. You get to focus on this great big crescent sun. It doesn't have a defined point like a star you can focus on, you see. Okay. We need to obtain photometry of beads simultaneously in red and blue, as I did. The study needs to be repeated without the errors that I pointed out. I shouldn't call them errors, but without the deficiencies that I pointed out. Secondly, we can use a large aperture to minimize scintillation effects during photometry while decreasing light throughput by using narrowband filters, and thereby get more accurate measurements of the beads by decreasing the scintillation effects. In fact, if you use a small telescope and a large telescope at the same mounting, at the same observation, you can identify the scintillation effects because they change more on the small telescope than they do on a large telescope. And if you're good at mathematical analysis, you'll be able to subtract the scintillation effect and find out whether you have any underlying diffraction rippling. You see what I mean? Now, I don't expect that it's going to be very accurate, but somebody needs to do this. I'm trying to give you the concept. Let's think about it, okay? Next, we need low-resolution spectra of the beads while simultaneously obtaining photometry. You don't want to just go do photometry and compare it to some other telescope across the, 500 yards away from you with his spectrograph. You want to do it from the same mounting to eliminate a lot of error, okay? And that way we can see whether we're studying Baily's beads that are actually in the chromosphere. And it's not necessary to include many beads in this. You don't have to have all the beads. You really just need a few. To my knowledge, it's never been done. Next slide, please. 10 nanometers. They're made by Edmund Optics. Okay. All right. Now, I've been to a few eclipses, and I just want to say, for those of you who are challenged by this and want to consider doing it, you must use a clock drive with a hand controller. Don't try to follow it with your hand. David Dunham's paver stone idea is going to help me do eclipses in the future, because one of the bugaboos is that it takes me hours to set up my equipment and fiddle with it and make sure it all works and get it focused and look for ghost images and change the filter angle so I don't get a ghost image, and darn it all. And by the time I'm focused that one, I'm not well polar aligned and it's out of the field. You see, you can't align your telescope in the daytime. So what I'm going to do in the future is I'm going to use paver stones or something equivalent thereto, and I'm going to go out at night, the day before the eclipse, set up my equipment, get it polar aligned, mark the ground where my tripod legs go, and then when I come back the next day, I'll be polar aligned and I won't waste so much time repointing the telescope when I'm trying to focus. You see what I mean? All right. So, you get some ideas by experience. All right. Secondly, I'm going to use a Hartmann mask to help me focus, because focusing on the sun is very difficult prior to the eclipse. Use a full aperture solar filter that should be tilted a few degrees. The source of the scattered light and the integrated light, the one on the lower right, I believe, was reflected back from the back of the shiny full aperture filter. And so what I want to do in the future is have a full aperture filter that's slightly tilted. The full aperture filter is much less sensitive to direction and tilting than the narrow bandwidth filters are. You don't want to tilt those. They're very sensitive to tilt. All right, and finally I want to point out something about not combining multiple video outputs onto a single recording device. That's going to be fraught with errors, as you saw, making my green thing too faint. Next slide, please. All right, now I'm done. There are a lot of you who are quite knowledgeable about solar eclipses, and I thought before I take questions, I should take answers. Does anybody have any ideas they want to share about this that can help us deal with these problems? Tony?
Okay, so I'll offer two points of input. We were trying to fit a curve to that. We were checking second order equations.
Yeah.
Third order equations. Work that I've done with Bob Anderson and his modeling and shooting models and data. Switching between the second order model third order model, you're always going to get a better least squares fit with the third order model because you added an order of variability.
Yeah. Okay.
So you may want to talk to Bob Anderson about that, but there are ways that you can normalize out the number of orders of variability. And he's doing it with doing the maximum likelihood calculation. He's doing it with the IOTA information criteria.
Yes. Well, thank you for that insight. And just for the people who are online listening, I want to repeat that Tony George has pointed out that he's done with Bob Anderson some work on light curve fitting with power functions, second order and third order and other orders models, and that he points out that you'll always get a better light curve fit with a third order model than a second order model. And I see that point, and thank you for clarifying that. But the reason to use second and third order models and not a fourth order model, which would give you a better light curve fit, a fourth order would give you a better fit. The reason to use second and third order is because of the analysis that I showed, that in principle, with the brightness of a bead shining through the mountains of the moon, in principle it should fit a second or third order model depending on the shape of the gap. And that's why I would use those two. So that's why I just wanted to say that.
My suggestion is to use the IOTA information criteria absolutely for whether the model is right.
I see.
Because you're introducing an extra fit.
Yeah. Well, say it anytime you want. Any other answers? Steve?
Certainly not the solution.
Uh-huh. Okay. I'll look you up. Terry? Okay. Anything else? Are we any questions from the outside folks? No. Richard? I'm not sure I'm going to be able to repeat what you've said for the folks who are online. So Richard is saying that we need to try again on eclipses with narrowband filters, and?
And with your pre-application, I think, you can do calculation,
yeah.
And,
all right. Let me say that, yeah, so we can correlate the data with the Picard satellite data. Let me say that, I've read a number of articles about data from the Picard satellite, and I just want to say that I think it's fundamentally disappointing, and that the data of solar radius measurement from the Picard satellite is really bothered by several noise factors. One of them is the thermal changes in the instruments, and there's also its problem with diffraction in the instrument and so on. And I'm not sure it gets around the problems that I presented, and I'm skeptical that it's actually more accurate than our Baily speed observations. So pardon my skepticism, but I just don't think it's much better than the other data. I think the satellite has been a disappointment for astronomers. Okay. Let's see. Walt?
I relate particularly to the focus of really next focus on the sun.
Yeah.
Is it feasible to focus on a star the night before and see what alternatively create an artificial star so you can focus on something like that?
You know, to some extent that Walt first of all stated his experience similar to mine with trouble focusing during an eclipse, and asks whether it's feasible to focus on a star the night before. Let me say that whether you do that in part depends on the type of telescope you use, because in some telescopes, refractors, it may be that the focus is very color dependent. And in some telescopes, especially, I think, well, probably both refractors and reflectors, focus is very temperature dependent. And if it's cool at night, and then, you know, you focus at night, then you're going to discover that the focus is different in the daytime. This is a big problem, and astro imagers are struggling with it right now. You know, they have temperature, they make temperature graphs and get it into their software that controls the focus, automatic focus on their imaging software, so that they actually change the focus with a servo motor according to the ambient temperature. And so I just want to say that focus is a significant problem, not just for us, but for other astronomers, and the temperature is going to be a bugaboo for you in that. Tony?
Yeah, so I have two more comments then. Basically, in the last hour of the Jupiter usual events, I did a lot of recordings with classes being 45 to 60 minutes long. And during that period, my Schmidt-Cassegrain telescope would change focus so radically that I would change a sharply focused moon to a blob because of the temperature drop over that period of time.
Yeah. And then if you try to focus, you mess it up. You miss data. Yeah. Right.
And then the other comment was, you mentioned the issue about scintillation effects, and Bob Anderson has done a lot of research on that with some testing that I've done, and it is very easy now to determine the amount of scintillation effect by looking at the noise data. The scintillation effect causes autocorrelation of noise, and it is now very simple to analyze that, and we can work with that.
Yeah. I have some data on that too, but I'm not going to ever publish it because I don't know the formality of the math. And so, you know, it's just one of those things, that information that I've gathered over the years. But thank you for pointing that out. Tony, for the benefit of those online, Tony was pointing out that Bob Anderson has been working on some mathematical ways to analyze scintillation to ascertain how much of the noise and what parts of the noise are due to scintillation effects. Bruce?
It's occurred to me that rather than using neutral density filters, primary camera is much faster than there's some of these faster CMOS cameras that can go 500 frames or something like that, and there you'll have a lot more frames to analyze. You can do some essentially spectral interferometry and analyze your data mathematically to reduce a lot of the atmospheric problems.
Interesting. Bruce Holenstein points out that we have faster cameras now, CMOS cameras that can go up to 300 frames per second, and that these would enable us to do some speckle studies that may actually enable us to identify noise and scintillation effects and reduce it in these observations. Thank you for pointing that out. It's something I'm ignorant about. Terry.
The solar benefit for a number of guys in the room, and we took about 40 scopes, but it's a standardized aperture. You commented on going to larger aperture scopes and having all the scopes preferably on the same mount to control some of the variations.
Yes.
I'm curious what you would recommend for
Well, scintillation is rough. Scintillation, from the standpoint of its amplitude, is roughly proportional inversely to aperture. So if, you know, a good way to do it would be if you're going to have say I have a nice mounting for my 11-inch Schmidt Cassegrain, that's 280 millimeter aperture, and then I could have a quarter of that, which would have 4 times as much scintillation. So a quarter of that would be an aperture of, say, 55, 56 or something millimeters, and use that as a scope mounted piggyback on the 11-inch scope, and then compare the data from the two to identify by analysis how much of the noise is scintillation, and then adjust the light curve accordingly. There was a question online. We need to handle that one.
With the flocking that Alton, Oregon has for it fits into the nose piece of video cameras, solve any of the scattered light issue.
In my opinion, it would not. I think that at an eclipse, the scattered light that the flocking helps is light that is coming in at a substantial angle, like half a degree different from the light we're wanting to analyze. And that light will strike beyond the CCD chip and reflect inside the video camera and the focusing tube and so on. And in an eclipse, that light is blocked by the moon. So I just think that we don't have that particular scattered light problem, and the scattered light that I think we're getting is reflected off the optics itself. Okay. Okay.
Elizabeth asked about.
Yeah. Well, you know, I'm sorry we're behind. Does Elizabeth have a